My name is Timur Doumler. I'm a developer advocate at JetBrains. We make the C-Line IDE and lots of other cool developer products. I'm also one of the co-founders of Cradle, music tech startup. We just released a new product called The Spirit. It's really cool. Check it out. Also, disclaimer, as Jules already said, I just flew in from a place which is 10 time zones away. So I'm really, really jet lagged and I haven't slept in a long time. So I don't know how this is going to go today. Let's see. But yeah. Cool. So we're going to talk about RCU. Let's just dive right in. Here are the assumptions. If you've seen some of my other talks, hopefully none of this is surprising. We have one or more low latency or real-time threads. Something like we do a lot in audio processing, but also in other places like gaming or high-frequency trading or other low latency applications. So this real-time thread or real-time threads, because we have these real-time deadlines, low latency, we need them to be lock-free, and we actually need them to be wait-free as well. So we can't take a mutex, we can't allocate memory, we can't call any system calls or anything like that. We can't do anything that doesn't have a deterministic execution time. And then the other assumption is that we have a bunch of other threads which don't have these time constraints, and they're just kind of normal threads doing normal stuff like GUI, maybe if you have music software, maybe MIDI messages, or write to file or to disk or read from disk or network or whatever. So we have all these threads, and then the other assumption is that this whole thing is running on some kind of consumer OS, just normal Windows, Mac OS, iOS, Linux, Android. So no special real-time operating system or anything like that. Just kind of usual kind of stuff where you would deploy your audio plugin or app or whatever it is. And so the problem kind of sounds simple. We have some kind of C++ object which is shared between these threads, right? So we have the real-time thread, one or multiple of them. We have a bunch of other threads. We have an object with some kind of value that all of these threads need to look at. And so the non-real-time threads in this particular setup are updating the value, and the real-time threads are reading the value, right? So here's an example. Any audio plugin, for example, will have this, right? You have a GUI, you have some gain or filter coefficients or whatever it is. You can tweak them with the GUI, you can rotate knobs, drag around a curve or whatever it is, and that's going to update the values. And then you want these values to feed into the real-time thread, which is generating your audio. And boom, you have this problem immediately, right? So you run into this inevitably. So how do we do this? Well, if it's just gain, that's one number, right? One floating point number. So we have that number there. We have the process, which is the process callback from our real-time thread, which is doing something with that number. It's reading it and applying it as a gain to like all the samples, for example. And then on the other thread, which is the non-real-time thread, you want to modify the value. For example, you had a mouse event coming in, it changed the value. You want to write a new value into that. Hopefully everybody here is aware that this is a data race. You cannot write into a variable and read from the same variable in two different threads. That's undefined behavior. It's probably going to work in debug mode. If you're on Intel in release mode, it's probably going to do weird stuff. And it's very difficult to debug these things. So what we can do is, as I'm sure many of you know, if it's just a number, we can put it into a std atomic. That makes it thread safe. So there we can load the atomic value from the real-time thread and then store into the atomic on the non-real-time thread, right? So that's all hopefully not very surprising. What if we have something which is not just a number, but something a bit bigger, like bytecode coefficients, 5 numbers, or maybe some other bigger object, right? So depending on what the object is and whether it's trivially copyable, if it's a string, for example, it's not trivially copyable, then this will not compile. If it is trivially copyable, like this one here, it's just a bunch of numbers, it will compile, it will run, but it will not do what you want because your CPU probably does not have the right atomic instructions to atomically swap 5 floats at a time. So your standard library is going to silently insert mutexes in there, and then if you do the load on the process on the real-time callback, you're going to lock a mutex, which you don't want. That's not good. So in order to guard yourself from this particular issue, should always add this static assert to check if your atomic with that particular type is actually always lock-free. And in this particular case, it will probably return false on your platform. So in that case, don't use atomic. Well, what else can we do? We cannot use a lock. Maybe we can use a try lock. So what we can do is we have our atomic again. Actually, in this case, I should have taken away the atomic. Imagine that the atomic is not there. I apologize for that. And then on the non-real-time thread, we can lock a mutex, and then the object is yours. You can modify it. On the real-time thread and a process callback, you cannot lock a mutex. That's not real-time safe, but you can try to lock it. And then if you succeeded, then you have the lock. So try lock is actually real-time safe. That's not going to block or anything like that. And then you can use the object. And if you didn't get the block, then you need to figure out some kind of fallback strategy. So I have done another talk here 2 years ago, just about this particular case, basically 50 minutes just about that. So if you're interested, you can watch that. There are a few problems here. One is that try lock is actually real-time safe, but unlock is not. And unlock is going to be called automatically when this lock goes out of scope at the end of this curly brace. And then if you have a std mutex, then that's not good, because mutex unlock might wake up other threads, and that's a system call that's not real-time safe. So you shouldn't be using a std mutex, you should be using a spin lock. And ideally, you shouldn't be using a spin lock that just spins, but a spin lock with progressive fallback. So one that tries a few times to get the lock. If it doesn't succeed, it sleeps for a while. If it doesn't succeed, it sleeps for a while longer, etc., etc. So that you avoid just hammering the atomic on one core in an infinite loop and just gonna suck your battery dry very quickly, and that's not very energy efficient. So you need a mutex like this with progressive fallback, and I've talked about how to implement those. But the other problem with this is that, well, the try lock can fail. Even if in this case, the unlock, if you have a proper spin lock, is real-time safe, you still may fail to obtain the lock. And then in that case, you just don't have access to that object. And you need to do something else. You need to, maybe you have an older value still stored somewhere. Is that okay to use an older value? I don't know, it depends on the use case, or maybe there's something else you can do. But it's not general solution, right? If you really need that latest value on the real-time thread, this is not a solution. Another thing that people use a lot is lock-free FIFOs. Lock-free FIFOs are great for passing a stream of data, like MIDI messages coming in or audio buffers coming in from the disk or something like that, like a steady stream of new data that you kind of consume. They're perfect for that. It's a very, very popular lock-free data structure in audio code. But can we use it for sharing an object with a single value, right? This is kind of what you want to do. Like we have an object with a value and we want to just share that, right? It sounds like it should be simple. But it turns out lock-free FIFO can work, is maybe not always the ideal solution. So you can do this thing because you have only one value that you want to share. You can create a lock-free FIFO with just one capacity 1, right? So it has maximum 1 element in it. So it's empty or it has 1 element in it. And then there's different types of FIFOs. You need, for this one, you need the one that overwrites when it's full. So whenever you already have a value in there and the writer puts a new value in there, it just overwrites the old value. And from the brilliant talk, Real-Time 101 by Fabian and Dave, that's the talk they gave at ADC 2019, highly recommended. That's a screenshot from that talk where we learned about different FIFOs and their properties. And in this case, we're interested in these ones here, where the writer overwrites on full and the consumer returns null and empty. And we see that in all the single or multi-producer or consumer combinations, actually the read is weight-free, so that's good. That's what we want. How could this look? Like we have a FIFO, maybe it has API, something like this. You can push into it. That's going to overwrite the previous value. And then you can pop. And then if the queue is empty, it's going to return you nothing. That's why it's optional there. And then we can create this weird FIFO with capacity 1. And then what we can do is we can, on the real-time thread in the process, we can pop that value. And we have to check, is there one? And if there is one, so the problem here is that we need to preserve a copy of the previous value in the real-time thread, right? sorry, and then if there's a newer one, we can overwrite that. And then that's actually a copy assignment or a move assignment, right? So in the case where it's some kind of trivially copyable structure, like the bytecode coefficients, it's gonna copy it into the real-time thread copy, which you might not want to do on a real-time thread, depending on how cheap it is to copy that object. It might be slow, it might be fast, depends, right? But you might not want to pay for this copy. And if it's something that has dynamic memory inside, like std_string or something like that, then it's actually even worse, because in that case, it's going to be probably a move assignment if you're doing this efficiently, but that's going to override the old value. That's going to be a deallocation, right? If that object has some dynamic memory inside. So you don't want to do that on the real-time thread. That's not good, right? You can't do assignment into something that deallocates and its destructor on the real-time thread. That's not real-time safe. So it's kind of weird. It might work in some cases, but like it doesn't work with multiple readers. That's the other problem, right? Because if you do the pop here, it's gone, right? The value is gone. And so if another reader also wants the value, it's just not there anymore. So it's not really good for this use case. And then, as I already said, it requires either a copy or a move assignment on a real-time thread, which you might not want to do. So what you end up doing actually is this pointer swapping thing. And this is what kind of the game you then end up playing. So instead of having an atomic object or something else, you have an atomic pointer to the object, because the pointer fits into word size. That's going to be lock-free. And then what you're going to do is on the real-time thread, you're going to atomically load the value of that pointer, and then you can dereference that pointer, do something with it. And then on the writer side, you kind of have to create a new object on a heap, and then you atomically swap the pointers. That's the exchange, right? That's like an atomic swap. So you atomically swap the pointers, and thereby you publish the new value to the real-time thread. And that's all lock-free, and that all works. However, when we do the pointer swap, on the non-real-time thread, we're left with this old value, the old coefficients pointer there. What are we going to do with that? So you can't really do, like, if you delete it right there, then you're going to delete it from under the reader, which is still reading it. So that's going to crash. That's going to be horrible. If you don't delete it, you have a memory leak. So that's also not good. So what do we do instead? And so the trick is kind of always with these patterns, delete the pointer not now, immediately, but at some time later when it's safe, somewhere where it's safe. And there's like a million different ways to do this. And basically the rest of the talk is about different ways to do this, and there are different trade-offs. And that's kind of where all the magic is. And kind of outside of the audio industry, there is this buzzword, deferred reclamation. That's what the kind of lock-free concurrency programming community calls this problem. That's kind of the buzzword. Yeah, you will find this in various books about concurrency and things like that. So there were some previous talks at this very conference and at other C++ and non-C++ conferences about this topic. In particular, I gave myself a talk called C++ in the audio industry at CPPCon 2015. That was actually my first conference talk ever. I don't know if anybody has seen that. And then there was another talk, which is one of my favorite talks of all time, ADC 3 years ago. Fabian, who is actually here, Dave, who, I don't know, is he here? Yeah, there you are. Hey, Dave. I really love your talk. It's great. We're going to talk about this talk a little bit later. First, I want to talk a little bit about my very first conference talk ever from 2015, where I actually presented a solution to this problem. However, that solution turned out to be a massive red herring. And so this is young me at CPPCon 2015. I said there that the solution to this, or a solution to this, is to use an atomic shared pointer. As it turned out, that's a really bad idea for many reasons. Now I know that 7 years later. Well, some of the reasons. Let's see, how would you do this with an atomic shared pointer? So back then I had to use these, it was C++ 14 was the current standard. So we had these like weird freestanding std atomic underscore store, and you had to pass in a pointer to a shared pointer, this weird freestanding functions API. In C++20, we have a much better API. We have std atomic of std shared pointer. That's just a class, so you can just use that. That's much nicer. It kind of has the same semantics, but it's just much better API. And so what we can do is we can create a new unique pointer on the writer thread and then atomically store that into this atomic shared pointer. And then on the real-time thread, we can atomically load that shared pointer and then use it. And because it's a shared pointer, it's reference counted, right? So we don't have to worry about the lifetime. It's going to be dereferenced. Sorry, it's going to be deleted exactly when nobody's using it anymore, right? So that's actually a problem, however, because you could end up, the audio thread could end up being the one who deletes it, right? And so that's not good. We don't want to deallocate on the real-time thread. So the solution I was talking about back then was to then have some kind of release pool, and then you like put the shared pointer into release pool, and then you like call that thing somewhere else on a timer on a background thread or something like that, and then it kind of just periodically like goes over all the shared pointers you put in there and deletes all the ones where nobody else is referring to them anymore. So that's kind of manual garbage collection, if you will. It has a few problems. One is it doesn't work if anyone is using weak pointer, because then you have this race condition of you are in this like reclamation pool thingy, and then it's like, oh, the ref count reached 0, great, I can delete it. So then it's going to delete it. But right in between, the weak pointer says, oh, I want to access this now, and it's creating a new shared pointer, increasing the ref count, and then you're deleting a live object from under that other thread, and that's horrible race condition. The bigger problem is, I mean, you can by convention say we're not going to use weak pointers, but the bigger problem is that all existing standard library implementations of atomic shared pointer are actually not lock-free, right? So they also have these mutexes inside. So definitely not real-time safe. Don't use that. It is possible to implement atomic shared pointer in a lock-free way. Standard libraries don't do that. It is possible, and I have done another 90-minute talk just about that, if you're curious, earlier this year at C++ Now. That's, I think, the best version of this talk. The C++ Now version, that's like 90-minute gory details of how to implement a lock-free atomic shared pointer. I'm going to spare you that here. I can tell you it's horrendously complex. I still haven't actually published my implementation because I'm still not sure I mean, I know it's possible because there's like 3 other implementations in the world that I'm aware of, which at least one of them seems to be correct because it's being used in production. So I think the algorithm is correct, but I just have to do a bit more work to like write all the test cases and everything. So I haven't published this one yet, but it's horrendously complex. I think it's the most complex thing I ever had to deal with. And the other problem with that is it's very slow, right? So it's kind of unintuitive. You're like, well, if it's lock-free, it should be fast, right? But it's not, because it has this like CAS loop inside, and every load is actually like multiple atomic operations. And so I benchmarked a couple existing implementations of atomic shared pointer back then in that 90-minute talk. And so the black one is the standard library version, or one of the standard library versions that has mutexes inside. And then the gray and the red are like 2 implementations of the lock-free one. And so the bars are kind of like the best case and worst case, and then the blob in the middle is like the average. And you see that the worst case for the mutex is a lot worse, because sometimes you just wait a lot to get that mutex. But the average case is actually really good, whereas for the lock-free version, the kind of worst case is better, because you have this like lock-free, you have guarantee that like at least one thread is going to make progress. So like you're not going to hit this like case where you wait forever. So the worst case is a lot better, which is what you want. But the average case is an order of magnitude worse than the mutex version, right? So it's not efficient at all. And not only is it not efficient, it's also not wait-free. It's just lock-free. So because you have this CAS loop inside, you actually don't have a deterministic amount of time within which even an atomic shared pointer load is guaranteed to complete. So it's an interesting beast, this atomic shared pointer, and it is maybe relevant for a few use cases, but that's not it. It's not a good tool for this use case. So basically, that was that about my talk. Don't do that. Let's talk about the other talk, the one by Fabian and Dave. And they had so much good stuff in this talk. And so actually they came up with a proper solution for this problem, one that actually works and is actually reasonable. And so here it is, maybe a little bit different. So I use snake case because I go to the C++ committee too much. So please excuse me for that. But this is kind of more or less what they presented in that talk. And I think it's a really good solution for this problem. So you have this atomic pointer there, and you also have the unique pointer. It's kind of tracking the same object, but the unique pointer is for the lifetime, and the atomic pointer is to for the atomic swaps. And then in the real-time thread, so the trick is you have this atomic pointer. In the real-time thread, you swap it with a null pointer to make the other thread know that you're using it. And then you use it, and then you swap it back, right? And then, so if you're not using it, you have the null pointer. If you're using it, you have the real pointer, and the other thread that has the null pointer. And the other thread, the non-real-time thread, is basically spinning on that pointer until that pointer is no longer a null pointer. And then when that pointer is no longer a null pointer, it means that the real-time thread is not using it anymore, and then it kind of slide in the new value. And then the old value gets assigned to this unique pointer, and then that goes out of scope, and that deletes it right there. I think the only complaint I have about this code is that this is, again, kind of this busy spin. I would do a spin with progressive backup there, because that's not going to burn as much battery and energy. It's just more efficient. But in principle, this is a very good solution. You can also wrap this into a very convenient, nice RAI interface. So Fabian showed us how to do this. He called it real-time object and put it into his library called Farmbot. I call it spin-on-write object, maybe in my opinion, maybe a little bit more precise. And it looks, my version looks slightly different, but it's kind of more or less the same thing. So you have the spin-on-write object, which kind of just wraps this whole logic. You create one of those, and then on the real-time thread, you do lock read, and then you get this read pointer, and that you can dereference it, you can arrow into it. And then when the read pointer, so when you get the read pointer, it's doing under the hood this atomic pointer swap, and it's putting the null pointer into there. And then the destructor, when it goes out of scope, it swaps it back. And then on the non-real-time thread, if you do the update and you give it a new value, what it does under the hood is it's kind of, you're doing this spin, and then when the pointer is no longer null pointer, it kind of swaps the pointers. And there is a slightly different API that you can also use if you don't want to update without new value, but you just want to modify a one-member function in there or something. You can get this write pointer. This is kind of how I use this. You do lock write, you get a write pointer, and then that lets you dereference into that object. Under the hood, it's actually peeling off a copy, and then you modify the copy, and then the destructor publishes the copy with this pointer swap. But that's all happening under the hood. So this is often a really, really good solution. And I think in many pieces of audio code, this is probably what people do. And this is working well in production. There's nothing wrong with that. There's a few trade-offs, though. So maybe for your use case, they're the right trade-offs. Maybe they're not, just depending on what you're doing, right? So the trade-off here is that the read is 2 atomic exchange operations. That's not the cheapest atomic operation there is. It's going to be slower than a load or a store. You can only have a single reader, which for audio is not a problem. But for gaming, for example, you want to have multiple threads rendering, so it would be quite limiting there. And the reader blocks the writer, which if the writer is a low priority thread, which just writes very occasionally, you don't really care about this. Or if the reader only just holds the read lock for a very short amount of time, you also pretty much don't care about this. But there's use cases where the read lock is held a bit longer, or it's a bit more important that the writer makes progress. And so sometimes you don't mind, sometimes you don't want the writer to be blocked by the reader. And then the other trade-off, the last trade-off, is that you can only have one writer, or if you have multiple writers, you have to put a mutex around the whole thing, and then they're going to block each other. And so the cool thing is that it's actually possible to get rid of all of these for trade-offs and improve on all 4 of them. It is possible, and I think that's really cool. I learned that only very recently when I thought about this, and I was like, there must be, it doesn't quite feel like the general solution, like, maybe there's something else. And I looked kind of outside of the audio industry, and I looked at what non-audio people are doing, and I found RCU, which is an algorithm that has been in use for a long time. It started in the Linux community. RCU stands for read copy update, which is, I think, a really bad name because all of these do read copy update, right? The spin on update or spin on write object is also doing read copy update. That's not the thing that makes RCU RCU. The thing that makes RCU RCU is it does read copy update and then it does deferred reclamation in a very particular way. And that's the thing that actually makes RCU RCU. So it's kind of a bit of a non-ideal name. As I said, it's used in the Linux community, it's used very, very heavily in the Linux kernel. It's been there in use for, I think, 2 decades or something, so it's not a new algorithm. There are also libraries available in user space that give you RCU. So one popular implementation is in the Folly library by Facebook. There is also a library called liburcu. There's like 20 different implementations of this. So it's quite a popular approach. It works really well if your reads are frequent and you need them to be wait-free, but the writes are kind of not as frequent, and you don't care as much about the performance of the writes. That's when RCU works really best. And the use case for RCU traditionally is not actually this sharing one object thing, but it's used as a building block to implement more complicated data structures like lock-free linked lists and things like that, where like one thread can rip out a node and another thread traverses it. And like you can imagine that in a Linux kernel, you need data structures like that. So RCU is really good to implement those. And actually, as of now, there is a proposal to add RCU to the C++ standard, which just last week at the committee meeting in Hawaii, we voted to approve. We approved the design of this. And it's now gone to the group that's responsible for just kind of getting the wording right. I think there will maybe be a couple design tweaks, but it's pretty solid. So my expectation is that it actually will be in C++ 26, which is pretty cool. That's the URL above where you can like read the proposal. It also has all the links to like existing implementations and stuff. And roughly how it works is you have a writer, right, which is writing new values, like value A, and then later it writes value B, and then later it writes value C. And then you have a bunch of readers. And they read, they take a read log and they read whatever the current value is at this point, right? And so reader 3, for example, takes A and keeps A for a little while, and then B is already the current value, but reader 3 is still reading A. And as long as reader 3 is reading A, it's not gonna be deleted from under reader 3, right? And so the way this is done is there is this notion of a grace period, which is a period, so it's a point in time. And then the grace period is the period by which all readers that had a read log at the start no longer have a read log, or that no longer have the same read log at the end. And so if you can identify such a grace period, then you know that all the objects, sorry, all the read logs, all the values to which the readers had read logs before the grace period started are safe to delete after the grace period ended. Okay. So how this is actually implemented, it's complicated. If you look into the implementations, it's pretty impenetrable what's going on there, but we're going to talk about this a little bit later. But this is the interface which is now being proposed for the C++ standard, and I'm pretty sure it's going to be in C++ 26. People are very excited about this. So what you do, how you do this, the same problem with RCU is you take a scope block with this RCU default domain, and it kind of behaves like a mutex, but it's not blocking anything. It's just this read log like before. However, notice that it's essentially like a global object. It's like a singleton. It has nothing to do with the value that you're reading, right? It's just global read log. So you take that, you do your business with the coefficients. That's the real-time thread. On the non-real-time thread, what you do is you do the atomic exchange like it did before, and then you retire the old pointer. And then RCU, because it remembers like read logs have been locked and released when, it kind of knows when it's safe to delete this pointer. And so RCU can handle multiple readers. Read is weight-free and it's very cheap. And readers do not book writers. So that's some very good properties. So this is very good stuff. There are some trade-offs though. One thing about RCU is that you have, in all the implementations and also in this interface that's been proposed for the standard, you have no control over when, how, and on what rate this reclamation happens. So for these systems for which this API has been designed, which is kind of these massive scalable systems like servers at Google or Facebook or whatever, that's fine, right? Because you have like hundreds of threads going on, and if you have like you probably have some kind of like a thread pool somewhere in the background that's doing the reclamation. You don't want to worry about that. You want the library to handle that. However, in audio, I think, at least in some use cases, you want to have a little bit more control over when and how this reclamation happens. Because if you're in an audio plugin, you don't want to have a library that just randomly spawns like thread pools all over the place, and you have no idea what's going on, right? You want to have tight control over what's happening. You want to say, okay, this reclamation should happen on this thread, on this timer callback or whatever, like in this way, right? So we want to have more control over this, which RCU doesn't give us. And then the other weird thing, as you saw, this read log of RCU, it's global, right? It's just reasoning about like what things might have been held here that can no longer be held there, but it's not per object. And that leads to a few weird properties. So there's actually another proposal which is not quite as far ahead as the RCU one. I don't think it's going to be in C++26. I think the design is a bit shaky, needs a bit more work. But basically the idea here is to implement something very, very similar to this real-time object or spin-on-write object kind of interface that we saw before. It's very similar, except it's meant to be built on top of RCU. So the way if we take this proposal and use the API in the way they propose it for the standard, it would look something like this. And the naming, I think, is also a bit weird. But naming things is hard, especially on the C++ committee. So they call this thing snapshot source. And then you create one of those, and then on the real-time thread, you would call get snapshot, which is the equivalent of the read log that we saw before. And then you get this thing back, which is the read pointer. And you can use that. You can dereference that, or like reference, like arrow into it, or whatever. And then on the non-real-time thread, on the writer, you do your update. You do your like atomic swap thing. So basically, how you do this with the API, you just give it a unique pointer to the new value. So it always has to be on the heap in this particular way. And then, I actually forgot a line here, a line of code. I'm so sorry. The next thing you need to do is you need to say coefs. So, damn it. So there is a call there where you do something like retire. No, actually, no. This is correct. Sorry, I'm all mixed up. This was with the bare bones RCU. With the snapshot source, it's correct. So you do the update, and then under the hood, it's doing the RCU retire for you. So it's like this. You can use it like this. It's like with the other thing that we use. So it looks very similar, but because it's meant to be on top of RCU, it has the same kind of trade-offs as RCU does. So you get multiple readers, which is good. Read is very cheap, which is good. Readers do not block writers, which is good. Again, you have no control over when, how, and like on what thread this reclamation happens. And the authors say that very explicitly, like this is not part of the design. This is just handled somehow, somewhere by the library. And then, if this is on top of RCU, you have this thing that the RCU domain is global. And if you map this onto this per object API, it has some really weird properties, and they actually call this out in the paper. If you take a snapshot pointer of a snapshot source, then it will not only block reclamation of that object, but actually it will block reclamation of all objects that were held at the point where you locked this one. So it's kind of weird, and there's like these cases where this can cause something like a reference cycle. And so I'm not sure yet whether like this is actually a problem. It just kind of feels weird. It might be okay in practice. But this one, I think, is the big one. Like for audio, you really want to like have control over how many threads you have and what they're doing. So at that point, I was like, okay, there's nothing out there that does what I want. So I need to implement it myself. So what I want is I want some kind of RCU-like object thing that supports multiple readers. Readers do not book writers. But then I want an explicit call reclaim, which I can put in whatever thread I want. And that's going to then and there look at the old values and see which ones can be cleaned up. And then I want this to be per object and not global. And so I went back into this principle and I said, okay, how would I implement this? Because at that point, I had no idea how RCU actually works, only the semantics of it, but not how you implement it. And so my first idea was, okay, well, so we have to figure out when like the read logs are no longer held. So let's just do reference counting. That's like the obvious thing, right? So whenever a reader reads a value, so we're gonna put the value next to like a ref count. So you have to either do that intrusively or you need to have a wrapper, which is a little bit annoying, but somehow you have the value next to a ref count. And then you just increase the ref count for the value that you read, right? So reader 1 is going to increase it, so it's going to be held by 1 reader, then by 2 readers, then by 3 readers, then reader 1 releases its log, so then it goes down to 2, it goes down to 1, and then in the end, it goes down to 0. And then whenever I call reclaim, like it just loops over all values and sees where's the ref count 0 and releases those. Sounds familiar? Well, I was like, I'm almost there, I'm almost done. And I have just one race condition that I just don't know how to resolve. And the race condition is basically the reader gets a pointer to the object, and then the next thing that it does is it increments the ref count of that object. But then, the reclaim can jump in between. So the writer can jump in between, swap out the value, and then the reclaim can also jump in between and rip it from out under you. And then that's it. You're reading a dangling pointer. And I was thinking about how to resolve this race condition, and it turned out it's exactly equivalent to implementing an atomic shared pointer. So it's just, at that point, I was just stuck. And then I asked my friends, Fabian and Dave, and they know things that I don't. And we had a very interesting conversation about this. And Fabian actually then said, hey, actually, I know how to do this because I've implemented this before. Let me show you how this works. And that kind of blew my mind. I was like, oh, okay, he actually figured this out. So I really learned something there. Thank you, Fabian. The trick is not to use reference counting, but to use something that's called an epoch counter or generation counter. So whenever the writer writes a new value, it increases this epoch count. So a new epoch starts with a new value. And then what the readers do is that whenever you get the read log, you remember at which epoch, which was the current epoch when you got the read log. And then when you release the read log, you set your own kind of epoch to 0. And that's a sign that you're not reading anything. And then when you start reading again, it's like, for example, with B here, that's epoch 2. So you just say, okay, reader 1 is at epoch 2. And then whenever a reader is done with an object, it retires it. So it puts it on a zombie list. But then it remembers what was the current epoch, not the current epoch, what was the epoch of that object when that value was read? What was its epoch? And then the reclaim, whenever you call the reclaim, it loops over all these zombie objects, and then whenever there is a object that has an epoch that no reader has anymore, it can be safely reclaimed, right? So for example, here, when A was retired, it had epoch 1, but at this point where reclaim is called, reader 1 is at epoch 3, reader 2 is at epoch 2, and reader 3 is at epoch 3, so nobody's at epoch 1 anymore, so you can safely reclaim this value. And let's actually look at some code. So this is how you'd implement this. I call this the reclaim object. So it has the value, The atomic unique pointer is just like a little wrapper I wrote around this kind of thing where you have an atomic row pointer and next to it like a unique pointer for the lifetime, and you just kind of wrap this together. So that's nothing particularly interesting. And then the reclaim object has this current epoch, and that's going to be counted up every time you have a new value. And then it has a list of readers, and then obviously you also can have just one reader, and then the algorithm greatly simplifies, but this is kind of the generic case. You have a list of readers, and then you have this zombie list, where you put retired objects and the epoch when they were retired. The update creates a new object on the heap and does the pointer swap, which should be familiar by now, and then it the old value that's not needed anymore, it adds that to the zombie list together with the epoch of that at that point, and then it increments the epoch, right? So it increments the epoch, so a new epoch starts because you have a new value, and the old epoch is going to be put on the zombie list together with this value. And then the reader, you have to basically, because there is a reader list, you have to register and unregister the readers. So you have a list of readers, and then each reader, when you construct them, they have to register themselves. When you destruct them, you have to deregister them. And then what the read log does, it creates this read pointer thing, and then each reader knows its own epoch, right? And so this read pointer that's returned there, what that does is it stores the epoch, and then it reads the value, right? And then it gives you these dereference operators that you can access the value from. And so it says, okay, I'm now reading an object, and this is the current epoch. So it puts its own epoch counter there. And then on the destructor, I said, okay, I'm done reading, and then that reader will have epoch counter 0. That just means I'm not reading anything. And here's the reclaim. What you do is you basically loop over the zombie list, and then you erase, you say, does this retired object, are there any readers using the epoch at which this object was retired? And if no, delete the object, and then it just kind of cleans up the null pointers. And then this is the obvious thing, right? If you want to figure out if any readers are at this epoch, you literally just loop over the readers and look what the epoch is. And you also have to check. So if it's 0, then they're not reading anything, and if it's not 0, then you want to know if they're at an earlier epoch than this object. And if not, you can delete it. Now, you might ask yourself, and this is something also that Fabian pointed out to me, which I probably wouldn't have seen, is that's very interesting. So isn't that a race condition, right? So we take the current epoch and we say, this is the reader epoch, and then we load the value. But what if the writer increases the epoch in between? So we can load the epoch, and then the writer might jump in and write a new value in there and increase the epoch. And then we have the value of the wrong epoch in there. And actually, yes, it's a race condition, but it's a benign race condition in the sense that nothing bad happens. Because you end up with a value from epoch 6, and your epoch counter is 5. So the only thing that happens is that that object might be around for a little bit longer, because the writer thinks that you're in an earlier epoch than you actually are, but that's fine, right? So actually what this reader epoch means is not the epoch of the object, but it's the epoch of the object, or like the highest epoch that the reader might be at. So this is basically the whole implementation. It works as far as I can tell. And this is on GitHub. So actually, this is a little announcement. So Fabian and I, we started a little hobby project. We started a new library. It's called CRIL. Stands for Cross-Platform Real-Time I/O and Low Latency Library. And this is where we put our little real-time low latency utilities now. And it's kind of a project that we do together. It's fun. I'm learning a lot from this. Currently, on the main branch, there is only this progressive backoff spinlock that I talked about 2 years ago. But these, so I've written these two. We're going to talk about the second one in a bit, but the first one is the one I just showed. So It's not exactly done yet. Like there's some documentation missing and stuff. And Fabian hasn't reviewed my code yet. So it's on a branch currently in Timur/RCU, but you can already look at it and have a look at the algorithm. And then when we fixed all the bugs and stuff, then we're gonna merge it into main, hopefully soon. Right. So this thing also has a few trade-offs, right? So it gives you multiple readers. Readers do not block writers. This is good. Read is actually weight-free, and it's also cheaper than the spin-on-write object, right? Because the spin-on-write, it's 2 exchanges, but this one is just an increment and a set, which is not as expensive. So it's probably going to be more efficient than the spin-on-write object, even if you just have 1 reader. But there's also some trade-offs here. So the writer needs to do this heap allocation, which might be fine, might not be fine, depending on the use case. Writers block each other, right? So you have this mutex around the reader list and the zombie list. So you cannot simultaneously write from 2 threads. And then the reclaim also blocks the writers. And it turns out that, again, we can get rid of all 3 trade-offs. So we can actually solve all of this. I'm not sure if it's a good idea, but I'm going to, in the couple of minutes I have remaining, sketch out how you would do this. But before I get there, here's another algorithm which Fabian also taught me how to do. Hang on a minute. No, sorry. So, excuse me. I've just finished the slides earlier this morning. So here, writer needs to do heap allocation, writers block each other, and reclaim blocks writers. So first, you want to get rid of the writers block each other bit. Make writers not block each other. Turns out this is actually quite easy. There is this lock-free data structure, which is a lock-free, weight-free multi-reader linked list. And it's not a proper linked list. It only supports pushback and iterate. So it cannot never shrink. It can only grow. But because it can only grow, it's actually really easy to implement. You don't have to do anything complicated. And you can implement that in such a way that it's weight-free for arbitrary amount of threads. And so you can just make the zombie list one of those weight-free multi-reader linked lists that can only grow. The trade-off, so now it's going to be lock-free, and weight-free. Writers can write into it simultaneously. The trade-off is the writers become slower, actually quite a lot slower, because you have to traverse a linked list instead of just doing a pushback. So it's probably not worth it, because RCU is best if you're not writing that frequently anyway. But if you really want to, and that trade-off is important for a use case, you can make writers not block each other by using one of those linked lists. So running out of time, I'm going to overrun by a couple of minutes. I hope that's OK for you. So here's an alternative algorithm that Fabian also taught me, which has different trade-offs. I call it the reclaim on write object. I don't know, maybe there's a better name for it. So we saw in the reclaim object that we delete the expired zombies whenever we call reclaim, which you want to do separately, maybe on some kind of other thread. But you can also reclaim the expired zombies after every write. So a little bit like we did with the spin object before, right? So the writer waits for the reader until it's safe to reclaim. Actually, that has the downside now that readers block writers again, but it has the advantage that it's more memory efficient, because that doesn't require heap allocations. So maybe for some use cases, that's the good thing, right? If you don't have a heap, you can do this. But unlike the spin approach, it does support multiple readers, and so readers do not block writers actually is not true here in this case. Let me just remove this. And the read is still weight-free and cheaper than the spin on write object, because it's still like an increment and a load and not 2 exchanges. And so basically the way this works is very, very similar to like double buffering, where you just have 2 slots, and like one slot is basically the one that the reader is reading from, and the other one is the one that writer is writing from to. And then when the writer is done, it basically swaps the 2 slots and then waits for all the readers to finish reading the other slot, and then it's safe. So that's basically what it does. And so yeah, this is kind of an alternative approach. I'm almost done. With this approach, you can actually do something really cool. But before, you can actually use this for the other one. if you want to make reclaim not block writers, because this is also possible. So you can kind of take this approach, go back to the previous version, and use that approach on the writer side to make reclaim not block them. And the way to do this is, instead of using one linked list, you use two linked lists, right? So you have these two slots, and then the writers, when they retire objects, they push back into this one block-free linked list, and then the reclaim, when it wants to reclaim all of them, it atomically swaps the two linked lists, and then it waits for the writers to complete until none of the writers are writing into the old list anymore. And then it goes through it. So it publishes a new list, which is like just empty, and then new writers are pushing into that. The old writers might still be pushing into the old one, so it waits until there's no writers there anymore. And then it kind of traverses that, and everything that can be reclaimed will be reclaimed, and then everything that has to stay around will be pushed back into the other list. Right? And so in this way, we have readers not blocking each other, writers not blocking each other, reclaim not blocking writers, nothing is blocking anything. So that's kind of cool. In my opinion, it's overkill. Like, I don't know a use case for this. It is lock-free, but it's going to be more expensive, and like you're only going to hit that if you write a lot, right? And then at that point, you need some kind of back pressure on the writers. You kind of need to block them, otherwise you're going to run out of memory at some point, right? So it's kind of not what RCU is for. I think RCUs when the writes are not as frequent as the reads. So yeah, something to think about. There's many different ways to do this. Future work. I want to finish implementations of all the variations I talked about. They will be published on our brand new GitHub repository here. Bug fixes, optimizations. I really want to benchmark that stuff. Haven't got around to do that yet. And I want to hear from all of you how you solved this problem. Thank you very much.
When you have just a monotonically increasing epoch, do you ever worry about that running out so you get undefined behavior or a loop?
Yes, excellent question. So for this to work, you need the epoch counter to be in 64-bit integer. If with a 64-bit, so you need an atomic 64-bit integer. That's the requirement. If you have 64-bit, you're fine. I actually calculated this. If you have like 1,000 threads doing like each doing 1 million writes per second, then you're going to run out of counters in 300 years. So I think you're good.
What about those spaceships then?
But yeah, it does require a 64-bit atomic counter.
I look forward to hearing that in 300 years.
So Paul McKenney, the guy who wrote this RCU proposal and like knows a lot about RCU in the kernel, he published this paper with like about proper RCU, and there he has some strategy how to get around the counter wrapping around issue, but it's horrendously complex. I don't understand how it works. But I think there is a way.
Okay, any more questions?
Yeah, thank you for your talk. I'm just wondering other cases where mutexes or locks are fine to use an audio thread, because it's just tempting to do that because it's so simple, right? And I believe even Juice Framework has some places where like locks are used. And I'm just wondering if you have anything to say about that. But I'm definitely going to check out your library, because my conclusion is writing weight-free stuff yourself is pretty difficult, and you're still on a journey to keep improving, right? So could you say anything about that?
It's difficult because like most of the time it's fine until the one time when like the heap is going to be defragmented, and then it's going to take, you know, a couple of milliseconds longer than you have.
But you know that's someone on a Windows 98 machine. They're probably not on the internet to send you a complaining email.
So I would actually be very interested in a talk where somebody says, let's just do this and see what happens, and like benchmark it really well and like figure out what the cost of an allocation actually is. Like that would be a talk I would like to see. I don't have an answer for you right now.
Okay, we'd better clear the room and everyone. Thanks again, Timur.
I'll be around so you can ask him more questions. Thank you.